Hey everyone, and welcome to the second interdisciplinary session for set theory. So this session will be concerned between linking set theory and biology. So if you recall, the last interdisciplinary session was linking between set theory and probability theory. So this session will be concerned with biology and genetics in specific. So first, the main concern that we'll be having in developing this model would be predicting the possible genes of the offspring through the genes of the parents. So given a set of genes that the parents have, I want to know what possible set of genes could the offspring have. The tools that we'll be using are set theory and cross product, both the old definition and the functions definition, which were explained in previous videos and in previous classes. So some of the terms that we'll be using is first phenotype. So phenotype are the observable traits on an individual. We will not be hugely concerned with the phenotype in this class. However, we will just use the term a few times. Genotype is the collection of genes of an individual. A gene is a discrete unit of hereditary material. So of course there could be more accurate definitions in terms of structure and such things. However, they are not of huge concern for the set theory class. Alleles are alternative versions to genes. So for example, you could have the gene that determines the eye color, and so the alleles would be the cause of having blue eyes or brown eyes or whatever. So these are the same gene and usually in the same locus, but they just generate different versions of a certain trait, so different eye colors, for example, assuming that eye color is only controlled by one gene, of course. Homozygotic are a pair of it's just any individual that has a pair of identical alleles. Heterozygotic is just the not homozygotic version, it's just having two different alleles instead of the same pair of alleles. So when Mendel made few experiments, he will just roughly explain the two observations that he had when he was just mating few plants that he had. So the first is that the phenotype of the first filial group was equivalent to 2 times phenotype of the parents. Now, this will just become clearer in a second when we go through the example, but just bear with me for the moment. And the second observation that the phenotype of the second filial group occurred in a 3-to-1 ratio. So, for example, if their parents had white flowers and purple flowers, and assuming, of course, that they were of equal numbers, so 50% white flowers and 50% purple flowers, when Mendel mated the plants of these two flowers, the first filial group or the first generation of children or offsprings all had purple flowers. So that just explained the first observation. This second observation talks about the second filial group or the second line of offsprings. So that results from the mating of the first filial group together. The result was that every 3 purple flowers had 1 white flower in return. So the overall ratio is 3 purple to 1 white, or 75% purple and 25% white. So he just had few conclusions. The first, that the white trait did not totally disappear because the trait appeared again in the second filial group. So the cause of the white trait must have been just hidden or inhibited. The second is that purple is dominant and white is recessive. Now that just defined that there are 2 different kinds of traits, which should be useful when we are developing our set theory model. And the third is that hereditary is discrete, which is actually crucial in our model. Had the old thoughts of the idea that genetics is more like fluids that mix together to form a new set of traits, the whole set theory model would immediately collapse. So the idea that hereditary is discrete is really crucial to developing our set theory system. So Mendel's model just depends on few ideas. First, that different versions of a gene cause different traits. The second, that two copies are inherited from the parents, each from every parent. The third is that the dominant allele determines the phenotype, which is not, again, of a huge concern for us in this class. And the fourth is the most important for the set theory, which is that alleles separate. So we will be able to form ordered pairs and such things. If they would not separate, we would not have been able to develop this model at all. So the first example, assuming that, so R capital always stands for the dominant trait and R small just for the recessive trait. But again, we're not hugely concerned with the phenotype, more with the genotype of the offspring, so that would not be of a great importance. And here R just does not really stand for a specific trait. So in biology, we would really won't wish to know the trait. However, in set theory, we just consider that there is a dominant and recessive one, or that they are just a little different and nothing more. So how we are going to approach this problem in terms of set theory? So normally in biology we would use Punnett squares. However, we will demonstrate in a moment why Punnett squares will not always work in some cases. But just for now, we'll just develop the set theory model for this case. So we'll just define two classes: A1, which has R capital and R small, and this just represents the left parent, and A2 is also happens to be the case that it's equivalent to A1, which is R capital R small, but it could have been just different. Now we'll define also the indices class, which is just 1 and 2. So this is just the class of the indices that you have, 1 and 2. Now, the way we defined Cartesian product in its most general form is that it's all if f of I belongs to a sub I. So f of 1 belongs to a1 and f of 2 belongs to a2, and it's just a set of all possible combinations out of this function. So for example, in this case, you'd have that first I could be 1 or 2, so that's just the class of entity that we have. Now we are going to assume that f of 2 is constant and equivalent to R capital, and see what the possible values that f1 could possibly have. So in our case, f1 could have either R capital or R small. Now we are going to next assume that f of 2 equals R small and see what possible values f1 could have, and we find that it's also R capital R small. So overall we have actually formed 4 different possible combinations, which is R capital, R capital, R small, R capital, R capital, R small, and R small, R small. So that's just the definition of the Cartesian product. So these are just the set-theoretic way of writing it. So the period that we will have are R capital, R capital, R small, R capital, R capital, R small, and R small, R small. So the first element of the pair represents the father or the first parent, and the second element represents just the second parent or the mother. So that's if you want to find all the possible combinations. However, if you only want to find the distinct or unique combinations, we're just going to assume that the ordered pair of AB equals the ordered pair of BA for all A and B. Now, if also you recall in previous classes for set theory, we said that the only difference between a doubleton or a class of 2 elements and an ordered pair is that they are ordered. So really this just transforms every ordered pair into a class. So like this final result. So this S maps to, so they are not equivalent, but this can be mapped to that S using this rule. Okay, so the final result that the unique combinations we have are R capital, R capital, R capital, R small, and R small, R small. Now, you might have used the older method of Cartesian product. So again, starting with A1 equals R capital, R small, and A2 equals R capital, R small, you could have just taken the first element from A1 with the first element of A2, and this gives you the first element of A1 cross A2. Then the first element of A1 with the second element of A2. Then the second element of A1 with the first element of A2. Then the second element of A1 with the second element of A2, and this just forms you all the possible ordered pairs. Now this would always work for the case of 2 products together. However, when we move to 3 products together, this method will not, the old method will not hugely work. However, the function method is the most general form and can work to any number of cross products that you'll have, to the cross product of any number of classes you wish. And that's why I prefer using the first method, especially on a huge number of classes. Then we have the multiple traits. So assuming that this time we will be dealing with multiple traits. So for example, R capital, R small, G capital, G capital is crossed with R capital, R small, G capital, G small. Now I will do at the same, but I will solve 2 problems simultaneously. The first problem is R capital, R small with R capital, R small. So that's the first problem. And then the second problem is G capital with G capital, G small. So again, we do as before. We define A1 R capital, R small, A2 R capital, R small. Then we form the cross product, and overall just gives me those elements right here. So these are the distinct ones. Of course, if I want to find all the possible combinations, I will just leave the ordered pairs. However, in this scenario, I'm not concerned. I just want to know all the possibilities, and I'm not really giving much concern to the relative frequency or the relative probability of each of these. Now, we'll do the same with B1 and B2. So B1 is G capital, the first parent. B2 is G capital, G small, the second parent. Then I form the cross between B1 and B2. And so, again, after just forming the cross in the same manner that we formed it before, the end result is that the unique or distinct elements in B are G capital, and G capital, G small. Now the last step is to take the cross product between A and B. The Cartesian product between A and B. So this will just give me R capital with G capital, and then you'd have R capital with G capital, G small. Then again, the second element, doing the same thing with the second element, you'll get the R capital R small with G capital, R capital R small with G capital G small, and the same thing, of course, for the third element. So overall, these are the different or distinct combination that you'll have, which is R capital G capital, R capital G capital G small, and the same thing for all the R combination that we obtained. Now, in general, you'll actually get 16 possibilities, but again, not all the 16 are unique. So these are only the unique ones, but some of these will be more probabilistic than others. However, if you want to know every single one, you could just skip this step over here. So we would have left A with 4 ordered pairs and B with 4 ordered pairs and form the cross product between these. You'd of course get similar results. So for example, taking the first element of A with the first element of B would give R capital, G capital, which is the same as the first element of A with the third element of G, R capital, G capital. So you would have two. So here you would have two offsprings with the same exact genes. So in here they were omitted, but overall you'll get 16 number of offsprings. Okay. Now we'll be concerned now with 3 traits together. Now the reason why we are giving this example is because this really demonstrates why Punnett squares will not always work, and the second thing because it demonstrates why the new definition of the Cartesian product based on functions is actually much more useful than the older definition. So again, as always, we'll proceed with A1, A2, so R capital R small, and the same thing for B1 and B2, and C1 and C2, so the different traits that I have. Now I will define S1 as the cross product between A1 and A2, S2 as the the Cartesian product between B1 and B2, and S3 as the Cartesian product between C1 and C2. And I'll just write these products down. Now, in order to find all the possible combinations, I should form the Cartesian product between S1, S2, and S3. So now I have 3 classes that I want to find the product to. Now, overall, the number of offspring that you should have is 4 by 3, which is a huge number. And it might seem that you will get lost trying to construct every single one of these. However, we'd actually construct every single one of these, and then at the end I will tell you a method that would immediately solve the problem for any number of traits, not just 3 traits, 5 traits, or any number of traits. Assuming that the number of traits are from both parents are equivalent, which is, I think, is the actual biological case that happens. So again, I define the class of indices 1, 2, and 3, and I have my S1, S2, and S3. Now, the table that I'm going to show in a second will be a little bit complicated. However, just bear with me till I explain each one of these. So, the method that I'll be using is that I'm going to hold F2 and F3 at constant at the first element. So F2 is G capital, and F3 is Y capital. And then I'm going to variate F1 through each element of S1. So R capital, R small, R capital, R small, and R small. Now, so that's the first table right here. The second table, I'm going to do the same. However, I'm going to hold F2 constant at G small, G capital. So first I will hold F3 constant also, Y capital at the first element, and I'm going to variate F1 as in the previous table, R capital, R small, R capital, R small, R small. However, I'm going to change F2. It is going to be also constant, but at the second element of S of 2, which is G small, G capital. Now, I think you probably guessed what will happen in the third table. Just the same, F3 is constant at Y capital, F1 just variating as always. However, the F of 2 is now held constant at the third element in S2. And of course, the fourth table is just the same, but the F2 is held at the fourth element in S2. Now, the next step would be to repeat the whole previous slide, however at f3 held constant at the second element. So what I'm going to do is, again, f1 is always variating through every element at each step. So R capital, R capital, R small, R capital, capital, R small, R small, R small, and then I do recycle again through every single column in these tables. Now, I'm going to do it as I did before, but I'm going to hold f3 constant at the second element of s3. So the second element of s3 is y small, y capital. So holding this constant, f2 is going to at first be the g capital, which is the first element of s2. Now the second table, again, f3 is still holds constant at the second element in s3. Now this time, and f1 is still variating as it is, f2 is held constant at the second element in s2, which is g small, g capital. Now you can already guess what I'm going to do in the third table, which is still variating f1 through each of its through each element in s1. f3 is still held constant at the second element in s3. Now, and f2 is the third element in s2. And the fourth table is the same, but just f2 is at the fourth element. Now you can guess what the next table would look like. f3 would be held constant. I'm going to repeat this whole slide, and the same thing with the last slide. However, f3 will be held constant at the third element in s3, which was y capital, y small. So going back, y capital, y small. And then I'm going to, as always, variate f1 through every element in s1, and f2 would at first, for the first four columns of the first table, be held constant at the first element in s2, g capital, g capital. In the second one, again, still f of 3 is held constant at the third element in s3. f1 is variating through each column, and f of 2 is just the second element in s2. The same thing for the third table, and the same thing for the fourth table. And again, the last four tables is just the same, but f3 is held y small, which is the fourth element in S3. Now, I would like to draw the similarity between it and the truth table. In the truth table, if we had three inputs, now here S just represents for something, because I'm not care about the output in this case. So if I hold P, so if I want to find all the possible combinations of true and false between these three statements, I first variate P node, or the P0, every single time. So true, false, true, false, true, false, true, false. P1 variates every 2 power 1, so which is equivalent to 2. True, true, false, false, true, true, false, false. And P2 variates every 2 power 2, so which is 4. True, 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 false, 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 false. Now this guaranteed that I got all the possible combinations between P2, P1, P0, assuming that they can only get true or false values. In general, Pn is just variates every 2 power n turns. Okay, so P1, so 1 here, plugging 1 for P1 would be 2 power 1, which is 2. So true, true, false, false, true, true, false, false, etc. This works for any finite number of statements. Now the same thing actually will be happening in this case. However, we'll be concerned with powers of 4. So the first one variates as 4 power 0. So it variates every single turn, and then it recycles back. Actually, when you finish, you just recycle back. So R capital, R capital, R small, R capital, R capital, R small, R small, R small. Then again, R capital, R capital, R small, R capital, R capital, R small, R small, R small. The second one variates. The second row that you have in all the tables will just variate as 4 bar 1. So 4 bar 1, so it variates every 4. So G capital, 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 G capital. And then, so these are the first 4 ordered pairs. Then again, it variates again. So it just changes into the second element after the fourth iteration, becoming G small, G capital for 4 times. And then becoming G capital, G small for 4 times. Then G small for 4 times. Then it recycles back. So it just alters it. So it just variates every 4 bar 1 times. You can already guess what happened to the third trait. It variates every 4 squared times. So if you count the number of columns over all columns in this page or in this slide, you'll find that they are actually 16. So F3 was held constant at y capital for 16 times, which is just the number of all the columns in every of these tables. Now the next one is it's held at the second element in F3 for 16 times, then for another 16 times, then for another 16 times. So it varies every 4 bar 2. If I had 4 traits, then the fourth trait would vary at 4 bar 3. Now you can just keep repeating this for any number of traits. So you can see that you can actually construct this whole table and you would get all the possibilities without having them all in mind. You can just type down the first row and variate it as about 4 bar 0, the second as 4 bar 1, the third as 4 bar 2, and the fourth as 4 bar 4, etc. and the nth trait is 4 power n minus 1 traits, and nothing more, and you'll get all the possible results. So actually, that's the end of this video. I hope that the ideas were just clear, and I hope that you can see why constructing this set theory model was helpful. Because, for example, in the case of 3 traits, I think you'll not be able to work with Punnett squares. You'll need to rely more on a Punnett cube, since you are forming a product between 3 classes. And of course, you can see that if you have 4 traits, you need to work in 4 dimensions, which I think is not really that easy, if it's even possible for us to work with. So that's it.